What is alternating current? In previous chapter, you have gone through this type of current. What current? That in any circuit, the current was constant. Say this is I naught, constant. So if there is a circuit, this is the suppose the resistance, and this is the DC source. So the current will flow like this, and this I is a constant. This is what we have seen in previous chapters. Suppose this is the resistance, which is R, and we call this type of current as direct current or DC. But okay, fine. First of all, let us plot this. So this is a constant current. So if this is the time axis and this is the current axis, so this is a constant current, and this value is I naught. Fine. So this is about the direct current. But now we are talking about something which is called as alternating current. What is alternating current, by the way? So to understand this, we need to understand that the power source that may be of two types. One is DC power source and one is AC power source. So in case of DC power source, if this is PS, in that case this is DC PS and this is AC PS. So DC PS generates a constant current, and AC PS generates some sort of current which is not constant. So in case of AC or alternating current, if this is my time axis and this is my current axis, so we can say that this current is not constant. The current is having some sort of variation over time. What type of variation? Is it periodic? Is it not periodic? That we will talk about it later. So this is it. In here I can say that the current which is generated by the AC power source is not constant. Constant with respect to what? With respect to time. Fine. So now if we go to the AC current, or not AC current, that is simply AC, alternating current. Let me write down for you what is alternating current. Okay. So this is the you can say one kind of definition. What is it saying? It is saying that it is a voltage or current which will be called alternating if it changes periodically with respect to time. By the way, what do I mean by periodic change? Periodic change, that means if I just draw some graph. So suppose this is the time axis and this is anything in the sense this may be current or this may be voltage. So periodic change means something like that it should copy, if we copy paste some part of the graph, it should generate the full graph. Fine. So time is always positive, so I am not considering this part is not considered. Only from starting from 0 we can assume that the time is there. So for example, if I have a graph like this, look at this. If I copy paste from this portion to this portion, from this point to this point, will I generate, can I generate the full graph? Yes, I can generate. Look, if I copy paste from this point to this point, I mean this region, what region? Look, this region, from this to this, then I can say that I am getting the full graph. How? Look, if I extend this more, then I will be getting this. The graph was actually like this. So this is the period we say. So this is the time axis. What is the period? This one. This range is the period, and we denote it with capital T. So the period is what? Capital T. Fine. So what is the period? The part which if I copy paste, I can generate the full graph. That is the period. And if there is some periodicity, we can say that the variable, it may be I, maybe V, that is periodically changing. And again, go to the this definition. What is this? It is saying that voltage or current is said to be alternating if it changes periodically its direction and magnitude. For example, this is one example where the direction is here, it is a positive direction, and here it's a negative direction. So the direction is already changing with respect to time, and there is a periodic nature. So if there is some periodicity, with respect to time, we say that is alternating. And what are the variables here? The variables may be current or voltage. So the current or voltage, they must be function of time, and not only function of time, they must be periodic function of time. Let me go through some of the examples which are important. Number one, sinusoidal waveform. Obviously, whatever we'll be talking, that will be applicable for current or voltage. So let me first write down the expression of the current. Let us just for now we let us uh, say that that is for current, and this is the form I naught sine omega t. Let's say this is the form. Sinusoidal means the sine or cosine, this type of thing. So this is simply the graph will be like, yeah. So this is the time axis, this is the current axis, and the graph will be of sine omega t. So yeah, you know the sine graph, and the amplitude will be what? I naught. The amplitude will be I naught, and in this side it will be negative of I naught. And this is the positive direction, this is the negative direction. So if I'm considering it time, then I say that this is the period, which is t. This is the period, so this will be what? T by 2. This will be t, like this. Fine. And here, look at this. If this graph was taken with respect to omega t, suppose, then what happens? Omega t, look at the expression. Omega t is what? It resembles like theta. So sine theta, we know the graph of sine theta, and if this is omega t, then we say that this point will be what? Omega into capital T, and this is nothing but 2 pi. And this will be omega t by 2, and this will be nothing but pi. So we can say that from this point, omega t by 2, it is pi, and omega t from this point, omega t equals to 2 pi. Both are indicating the same thing, that is omega t equals to twice of pi. Fine. Where the omega is nothing but the angular frequency. Another example, this was the first example. The second example is half. Example is half wave rectified waveform. What is this? We say in simply HWR. But rectified, this is rectified with respect to, or rectified from sinusoidal waveform. What do I mean? The graph is like, this is t axis, this is I axis. The graph from the sinusoidal. Rectified from sinusoidal means we are doing something with the sinusoidal, we are rectifying something, and we are rectifying in half wave. Half wave, we're rectifying the half wave. Let us understand what I want to say. So this was the sinusoidal curve, and we are now rectifying what? Half wave. We are rectifying half wave, I mean we are rectifying this part, half part. Rectifying means, just for your understanding, that we are considering one side only. One statement, we are considering the positive side only, so we will be considering the positive sides only, and we will be rectifying only the positive side. So we will not consider the negative sides. So what will be the look of half wave rectifier? Yes, this is the look of half wave rectified graph. So this is t axis. Here what is the period? Period is, look, if I copy paste from this region to this region, I will get the whole graph. So this is t, and if we resemble with the theta or omega t, then we can again find the same thing here, omega t equals to twice of pi. And what is the expression of this graph, mathematical expression? That is I of t equals to, it will be I0 sine omega t when t is from 0 to t by 2, and this is 0 when, it will be 0 when t is this. Just try to understand this part. This part is what? This part is I0 sine omega t. That's the previous thing. But this part in this region, this is 0. Okay, that's what I have written here. Fine. This is not the only part. You have to also consider that the periodicity. So this is the expression, but there we must impose some periodicity. Periodicity. Okay, plus periodicity. Why periodicity? This is the expression. This expression is only allowing me from this region to this region, but what after that? I have to be periodic. So that's why I have said we have to be considering the periodicity. But here, look at this expression. This is already periodic. Look at the expression. This is already periodic. We don't have to say that plus periodicity, because this is already periodic. We don't have to say that plus periodicity, because this is already periodic. Fine. Now the next example, that is what? That is full wave rectified waveform. And again, we are rectifying this. This is rectified from sinusoidal. And here in this example, we are taking, by sinusoidal means we are taking I equals to I naught sine omega t for this example. Fine. So here let me again draw some graph, that similar type of graph. So here full wave rectified. So what was the graph? The graph was I0 sine omega t, I mean like this. And we have to take care the full wave now. Full wave means we have to take this plus part also and this minus part, but after rectification. Rectification means all the graphs are in the same side. So we have to flip this one, make the negative the positive. Okay, again this is positive, this one is positive, so we don't have to rectify this, but this is again negative, so we have to again rectify this one to this side, and there is not this part. So this is the graph. Now look at this. This is also positive. Now all are positive. This is rectified. Here, this is not the period. This is not the period, because look at this. Because if I just copy paste this only, if I just copy this part and paste, then I will get the whole graph. So I don't need to consider this one, na? So the period here is this one only, t. Fine. Now what is the expression? Now here that is the first part from this one, that is simple, the previous one, I0 sine omega t. But for the next part, what I have to do, that is I have to look, before rectification this was like this, and after rectifying, I mean when I rectified this one, I am just flipping. That means that should be, this part should be minus of the same thing. Okay, so this is for the range t, and if this is t, then this will be what, twice of t, and this part is not there obviously, so I am just erasing this one. So here I have to write this t and twice t. So this is the expression, but again this is not the end. After that also we have to consider the periodicity, but we can replace this whole expression by this simple expression, that is I am taking the modulus value of sine omega t. So we don't again have to impose the periodicity because this is already periodic. Fine. Next example, next example, square or rectangular waveform. So here this is suppose the current or voltage axis, this is the time axis, and this is given like this one. The graph is given like this one. Here the period is from here to here. This is the period. Fine. And what is the expression? The expression is given like this, is very simple. The first one from uh, 0 to t by 2, it's plus it is plus I0, and after that it is minus I0, where when it is t by 2 to t. So when 0 to t by 2, and it's when, sorry, t by 2 to t. And not only this, we have to take care of the periodicity also. We have to impose the periodicity after that. Sawtooth waveform. The graph looks like, suppose this is I naught, this is minus I naught, and the graph looks like this. So here the periodicity is this one, t. And what is the expression here? You can simply write that that is t minus I naught when it is, I mean in the full period, in the full period. But after that we have to impose the periodicity. But if we want, we can replace this equation by simply this equation. Here we don't have to impose the periodicity externally, this is already periodic. This one is the box function, and you know this from your mathematics knowledge. So this was all about the examples of some of the alternating currents which are available. But there are some important terms which we are going to use often, that is the average and RMS values. Okay. First of all, how to find the how to find the average of any physical quantity, any physical quantity which is evolving with respect to time. So the general formula is, suppose y is the quantity and it is evolving with respect to time. So if we want to find the average, we say that the average, or we generally write that y average, this is given by y dt divided by dt. This integration is over the full range, but for periodic function, if y is periodic, in that case we say that the y average, it is simply given by, and the periodicity is t, then we say that this is given by this one. So this is the formula. And there is one more term, that is mean squared value. What is this? This is nothing but mean means what? Mean means average. So mean squared value means mean of squared values. Squared values. So if now y is the variable, then we need to find the mean of squared values, I mean squared of y. So this is the thing, y squared. So this is the formula, similar formula. Here it was dt 0 to t for periodic function if y is periodic, and in the upper side there was dt t, and when we were taking the average of y, then we keep y here, and now as we are taking the average of y square, we will keep y square here. So this is the formula. There is one more term that is very important, that is the root mean squared values. Root mean squared values. So we say that root mean squared as RMS. What is this? Y RMS is nothing but the root over of mean squared values. So if y is periodic, we say that y RMS is nothing but here dt 0 to t, and here it was y square dt 0 to t. So this is the RMS value. Now in alternating current, we have two variables that are of utmost importance, those are this I of t and v of t. So example, what is I average? This one. And what is this? This is nothing but t. So I can write this one as 0 to t I dt. Similarly, v average, what I will get? And for RMS values, I RMS, that is square root, again here I square dt, and here dt. So 0 to t, 0 to t, where capital T is the periodicity or the period. Fine. So here I will get like this, and similar goes for VRMS. So you can find this one as this. Generally speaking, that I naught is greater than that I RMS is greater than or equal to I average. Why I imposed the equal to sign here, here equal to sign? Because in case of the square waveform, the I RMS and I average both are same, that is I naught. What is I naught? I naught is the amplitude of current, and I think you can understand that I naught is amplitude. I mean this one, sorry, this one is I naught. Okay, fine. Here there is I naught. This is the amplitude. So this is the generally uh, which we can say. So you have to keep in mind this one. Let's calculate some IRMS and I average. For example, in case of sinusoidal waveform, the expression of I was like this. So first of all, let me calculate the I average. What was the formula? This was the formula. And okay, fine. Before going to this, if t is the time period, then this one is nothing but what? This one is nothing but average of sine omega t. You can understand that this is nothing but the average of this one, and this is given, and this is 0. You can calculate, but as this is going to be used everywhere, so I am not going to calculate it again and again. Here same goes for cos also. But for sine square, we have half, and similar for cos square also. Okay, and for half cycles, I mean t by 2, so 1 by t by 2. Let me just sine omega t dt is t by 2, that is nothing but twice of pi, and for half cycle t by 2, that is also twice by, I mean twice of 1 by pi. So you have to remember this, some of these formulas. So now fine. Okay, so if now we want to calculate this one, what is it going to be? Put the value of I. So I0 is a constant, that is sine of omega t dt, and it is like this. So I0, and then 1 by t, this one, this is nothing but this, so this will is 0. Fine. And I RMS is what? Root over of I square dt divided by t. So, and the integration limits are this: 1 by t, put the value of I naught square is a constant, fine, 0 to t, and try to focus on this part. So what I'm getting, this is 1 by 2, this is 1 by 2, so this is I0 by root 2. So for, okay, how is it 1 by 2? This is the formula, so I think you can get. So for sinusoidal, that is 0, and this is I0 by root 2. And the similar calculation will be there for sine omega t plus any phase factor for cos omega t plus any phase factor, I mean I0 will be there. Okay, let me just write down clearly. If I equals to this one, if I equals to this one, or if v equals to, again, if v equals to sine of omega t plus phi, or v equals to cosine of omega t plus phi, so for this all the calculation will be similar. I mean the I average will be 0, I RMS will be I naught by root 2, V average will be 0, and V RMS will be V naught by root 2. Now we can calculate this for half wave rectified and rectified from sinusoidal. Okay, let me not write it here because this is no more sinusoidal when it is rectified. So here we can calculate and we can show, and that is your homework. We can show, and if you cannot do it, we can explain this in the next class. That is, here I average will become I naught by pi, and I RMS will become I naught by 2. For full wave rectifier, we can get that I average is twice I naught by pi, and I RMS is I naught by root 2. For square or rectangular waveform, we can get that I RMS and I average both are same, that is I naught. And for sawtooth waveform, we can show that I average equals to I naught by not, this is I naught by 2. I average is I naught by 2, and I RMS is I naught by root 3. So I will suggest you, or not suggest, this one, and I mean HWR and FWR, these both are homework. Okay, fine. In reality, what AC ammeter reads, that is IRMS, the RMS value. It reads the IRMS, and AC voltmeter that reads that, oh, that reads VRMS value. But in this chapter, or in this standard also, we are only focused on this type of problems where the V is given by V naught sine omega t, and the corresponding I, which we will calculate, and we will find many more things, that is given by this one. So we are focused on the sinusoidal waveform.